What's up, scholars? We're going to take a look at an example problem to do with statics using our handy-dandy checklist. You'll notice I've got some weird effects going on from the window in my house. So I've got this funny rainbow effect. We're just going to roll with it. So I found number 18. I think it's a good one. It says calculate the tension in the wire that supports this 27 kilogram beam and the force FW exerted by the wall on the beam. Give the magnitude and the direction. So this is quite a step up from our first example, which was just kids sitting on a teeter-totter. Many of the forces were acting right on the pivot point. Here we're going to employ our handy-dandy statics problem-solving checklist to help us out. The first thing we're going to do is we're going to draw a picture and a useful free body diagram. The picture included in this problem is actually a pretty good free body diagram, so we'll start there. Alright, so I've started by drawing a very rough approximation of the picture. Remember, there was a string, we'll extend our wall here, a string that extended down that connected our little hanging beam. We're told that the mass of the beam, let's call that MB, was 27 kilograms. Now, importantly, remember we said that the weight of anything acts right at its center of gravity, so which is essentially the same concept as center of mass. So I'll add on here, we've got mg, and the final force, which is part of the question, is the force from the hinge. If you think about it this way, the tension is pulling this towards the wall. Because this has a weight here, it will want to rotate about this point right here, and it will be pulled towards the wall. So the wall has to exert an equal and opposite force, something like this. Now, to be clear, I'm going to call it FW, force from the wall. We don't technically know that angle yet. You might be able to see from symmetry that it's very likely going to be 40 degrees, but it won't always work out like that. So let's be careful and just call it theta. Okay, next we are going to make choose a convenient coordinate system, and we're going to pick a smart pivot point, which I'll point out in just a moment. We're also going to resolve the forces into vectors. We'll show that as well. All right, so excusing the psychedelic colors from my window, what I've done here is I've picked this point as our smart pivot point. Again, it doesn't technically matter what you pick, but this is going to eliminate the torques from this force since they act at this location. We're going to end up with just torques from the weight and the tension in the string. Now, I've already started to break apart our vectors. We've got the force, again, from the wall pushing back. We're going to break this into force from the wall in the x, that's that force, and the vertical force from the wall in the y direction. And then I've already partially broken tension down. The tension is going to very similarly have a tension in the y and a tension in the x. Now don't guess, pause, take a moment, think about it. SOHCAHTOA, sine theta is opposite over hypotenuse. So for the force from the wall case, the opposite would be FWY, the vertical wall force, over the wall force itself. And for the tension, sine theta for that is going to simply be opposite TY over T. Now we don't know what we're going to need out of this yet. I'm going to pause. We'll write down cosine, see if you can do that. So adjacent over hypotenuse, FWX over FW, the force from the wall in the x direction. That's the adjacent over the hypotenuse, and very similar for the tension, Tx over. Okay, so at this point you might feel a little bit lost. This is where we want to go back to our checklist. What's next? It says using letters to represent unknown forces, write down the equilibrium equations for these forces. So let's go ahead and do that. We want to write down the sum of the forces in the x direction. We know because this is not accelerating, it's not moving actually, that it's in static equilibrium. With the sum of the forces in the x direction, we're going to add up to be 0. That's also going to be true for the sum of the forces in the y direction. Now, this is Newton's second law for forces. And remember, that's the first equilibrium condition. It's not that important, like that's not a thing you're going to be quizzed or tested over, but it's nice to be able to go in steps, or you're always going to have access to that checklist. So let's do this. What are the forces acting in the x direction here? In fact, I'll add on to our original picture. We've got FWX, and we've got Tx. Those appear to be the only forces acting in the x direction. So let's pop those in right here. So we need to pick. In our coordinate system, let's have this direction be positive in the x direction and this be positive in the y. That makes sense. And then we'll also do the conventional, this direction we'll consider to be a positive torque. This will be a negative torque. That seems pretty reasonable. So here we're just saying counterclockwise, which is traditionally the positive direction, versus clockwise, which is going to be traditionally the negative direction. Okay, so the reason I ran into that roadblock, and maybe that's instructive, is I needed to figure out which one of these forces gets my minus sign. It looks like it's going to be positive FWX, and then I'm going to add to that a TX, but it's in the minus direction, minus TX, that equals 0. Okay, let's move on to the y direction forces. We've got an obvious one here. I'm going to do that in red so you can clearly see. We've got mg, that's acting down. We've got tension in the y acting up, and the force from the wall in the y acting up as well. So ty, and we'll call this fwy. Okay, so it doesn't really matter what order we take those in. We've got, let's just go ty plus fwy minus mg. That's going to be equal to 0. So at this point I actually already felt myself trying to skip to step 5, which is to solve the equation. And it just simply turns out that you can't solve it yet. So it's really critical here that now that we're dealing with torques, statics is tricky because you've got to deal with the forces and the torques. We do need to set up the torque equation. So let's do the tricky business of setting that up. You'll see why picking the pivot point that we did was really smart. So if the next thing we do, and I'll do it over here so we've got some room to play around, we'll section this off a little bit, is the sum of the torques is equal to 0. So we did this in a smart way. This force gets totally ignored because these forces are occurring at the pivot point. I know it doesn't look like this one is, but you can move the vectors wherever you want. It actually is coming out of right here. So we get to ignore all of this. The only torques are these 3 forces. You've got, actually only 2 of them. The tension in the x direction doesn't count as a torque because it's parallel to the pivot point. In other words, the only forces we care about in terms of torques are these. We've got Ty, and we've got mg. Now we need to do a little bit of work, and I maybe didn't write it down. We need to figure out where those are happening. As a reminder, torque is force times distance, or the lever arm times the force applied. So we do need to know what those locations of those forces are. Let me check that real fast. The reason I didn't write it down is because it's not given to you. It just tells you this information. So we're going to do this in terms of L, the length of the beam. We know that this is going to be L over 2, a distance away. I'm going to try to change colors, even though it's quite psychedelic here. So we'll say that the weight force acts at a distance L over 2, whereas these tension forces occur, I don't know how I'm going to sneak this in here, a distance, let's call it L from the edge. So all of the torques in the y direction, the torques from the tension in the y direction, those happen at a length L. This weight force happens at a length L over 2. So if we go back to our our torque equation, we've got T in the y acting up at a distance of L. So we'll call that Ty times L. And then that's acting torque-wise in the opposite direction from the weight. The weight is acting at a distance L over 2. So minus mg, that's the force, times L over 2, and that all ends up being equal to 0. There's one more big step that we need to do here in order to move this problem forward. The first thing we want to know is the tension in that wire. Now there's a couple places tension comes into play. You've got Tx, you've got Ty, you've got Ty again. Let's do this. Let's actually substitute in these tensions, or the trig information that we had. So we'll do one at a time. Let's start with the torques. So ty is right here. I'm going to solve for this. If I multiply both sides by t, I'll have t sine theta equals ty. So we'll rewrite this whole thing. So that would be t sine, I'm actually even just going to pop in 40 degrees times L. I'm going to move all of this over there by adding that whole term since it was negative. And that's going to be mgl over 2. Now some cool stuff happened there. You might actually be able to see how we can already get to the tension, but let's go about plugging in the rest of the information. I'm going to do it a little bit more quickly now. I'm going to pause and write them in. See if you can get it before I do. Alright, so I've done some rearranging. Namely, I plugged in the trig information. I did make one slight error that I want to fix. Up here I put sine theta. I'm actually just going to change it to sine 40 so we can avoid some confusion. So this is 40, that's 40. Here I accidentally wrote t cos theta. I'm going to switch that out for a 40, and I did that here as well. So anyway, we've plugged in all the trig information, and I've also eliminated these zeros by rearranging the algebra in a particular way. So the next step is, on our checklist, solve these equations for the unknowns. Now, we could just do this sort of haphazardly, but we want to do this in a smart way because, of course, the first thing we're looking for, yes, now we're looking at part A of this, is we are trying to solve for the tension. So the tension's hiding in this equation right here. This was from the torques. It just happened to be from the torques, by the way. It just worked out that way. So let's take this equation. T sine 40 degrees times L equals mg L over 2. Now we do have some information. We already know g, because that's 9.8 meters per second squared. We know m, that's 27 kilograms according to the wording of the problem. We get the angle, and here's the lovely thing. I actually came to this by mistake a moment ago, but they didn't give us the lengths. They didn't give us the lengths because we end up being able to cancel them. So all we need to do now is to solve for t. We're going to divide by sine of 40. So this will end up being t equals mg over 2. This 2 goes on the bottom, mg goes up on top, and this sine 40 degrees just comes down on the bottom with the 2. So 2 sine 40 degrees. We can calculate. This is how much tension this cable needs to provide to hold the thing up. So I put in all of that information, and I got 206 newtons of force. That is how much tension is required. So, for example, if this, whatever steel cable, for example, they were using to hold that up, if it was, had a breaking strength of 210 newtons and like a bunch of birds flew on this, it might end up breaking. So usually what they do to secure these is they'll add 2 of these wires to hold it up, as an example, if it's like an awning. So now you could have double the weight, or it would take double the amount of tension to break the thing. So, in fact, I took this picture when I was driving, or I wasn't driving, I was a passenger. This is a street light, and you can see it's a similar situation. The street light itself has a mass, the beam that's holding it has a mass, and then there are several support beams. There's one here, I don't know how well you can see it, very thin, and there's one on top holding it, and then there's actually like a counterweight holding it. So the people that design our infrastructure know all about this. They solve problems just like this all the time to make our modern world function. Now the next part wants to know the force from the wall. And looking ahead a little bit, I'm actually going to rewrite these in a way that's going to seem like we're moving backwards, but it's going to make some sense as we move forwards. So this, instead of calling it FW cos theta, I'm going to move back one step and just call it FWX for reasons that I'm hoping will become clear very soon, equals T cos 40 degrees. Now keep in mind we know all of this information. We can actually plug all that in and we'll get Fx for free. And then we can do the same thing here. I'm going to take this back one step and I'm going to leave it by itself. So we'll call it FWY. That's this thing. I'm going to move this T sine 40 to the other side. So it's going to be MGT sine 40 degrees. Now I'm going to tip my hand here and show you why I did that. At the end of this, we need to know a couple of things. We're trying to find the force, let me get that out of there, force on the wall, FW. Now, to be clear, we still don't technically know this angle, and what we want is FWY and FWX. We're going to use the Pythagorean theorem and some trig to figure out what FW, so we need to know what this is, and we need to know what this is. So I've gone backwards a step because what I'd really like to be able to do is say this. FW is just the square root of those added together. This is just the Pythagorean theorem. So at the end of this, I want those two things, and we'll actually have all the information that we need in order to make that calculation. We know that the tension is about 206. I've rounded that here, which might cause some errors, but we should be okay. It's 206 newtons times cos 40 degrees. That's going to give us this x component. And then we've also got FWY over here. That's going to be 27 kilograms times the acceleration of gravity. That should be a minus sign, sorry about that, minus this thing, t sine of 40. So that's going to be 206 newtons times sine of 40. So what's cool about this is we can punch all those in. In a moment, I'll have those numbers for you. So we've gotten that the horizontal wall force is 157.8 newtons. The vertical force, FWY, is 132 newtons. So back to our original picture, that's how hard the wall is pushing out and how hard the wall is pushing up in order to help keep everything in equilibrium. Now, as we've said, we are going to use the Pythagorean theorem and take the square root to get the force from the wall. So that I'm just going to write, it's going to be 157.8 squared, that's newtons, plus 132.2 newtons, all square, and that. So that ended up being 206 newtons rounded up, which gave us the exact same number as the tension. So I want you to be careful. That's not always going to be the case. It really depends on lots of the situation. The main reason that that happened here is because you basically only have two things supporting our beam. You have the tension pulling in this direction, and countering that you have the wall pushing back. You only have the weight of the beam. Now if we had additional weight, again I mentioned a moment ago, maybe some birds hang off the end here, then the wall has to, both of them have to work extra, but because of the way torques work out, it may not be, they may not stay perfectly balanced like this. So just keep that in mind. Now we also gave a hint earlier that the angle might be the same, but let's double check that. So one of the ways we can do that is we can use trig. We do know all three, but we can take the opposite over the adjacent, so that would be inverse tan of so opposite would be FWY over FWX, that's the adjacent. That's going to be our angle theta, and that will be the inverse tan of 132.2, 132.2 all over 157.8 newtons, those should cancel. 40 degrees. So after all of that, we ended up that the force from the wall being exactly equal and opposite in both magnitude and angle to the tension, which again is specific to this problem, so be careful. The last thing I want to say is that to go through all of this took the careful setup of us using our problem-solving checklist. Once we did that, it made solving this relatively straightforward, especially if you consider us just solving to the tension in the string portion of the program. Thank you so much.